Hello everyone. It's been a while since we last met. Today I'm gonna go through a past year paper, 2021-2022 Sem 2. So this happens to be my paper when I took the exams. Um yeah, this is to commemorate a 50 subscriber special. I didn't expect that I would continue to get much support after I stopped PTP, but still some people continue to subscribe even though I'm not pumping out any new content. And although my position as the PTP has ended, I guess the passion has never really died in me. And with that, let us get started. So, again, just to recap, this is 2021, 22, Sem 2. Okay, so let's get started. So, for the circuit in the diagram, determine the number of nodes, the number of meshes. Okay, so let's underline what we want. Number of nodes, number of meshes, and then number of independent nodes and the number of independent meshes. So let's look at the diagram and count the number of nodes. So what nodes do we have? Let's start from the bottom and then go swipe up to the top of the diagram. So starting from the bottom, we have the ground. So this is 1, 2, 3, 4, 5. This whole thing is 5 and 6. So we have 6 nodes altogether. Okay? So that's quite straightforward. This is 6. Now, the number of meshes. So, number of meshes is even easier to spot. So, how many individual closed loops can you see in the diagram? So, this is 1. This is 1. So, I'm gonna go assign the clockwise direction. This is 1. And then this is 2. Okay? Now, outside here, this is not considered a mesh. Okay? It's considered a loop, but it's not considered a mesh. Because within this, if you were to encircle this larger loop, right, you can find a smaller loop within itself, which is, this one. So it's not considered a mesh. So meshes cannot have any further meshes inside of them. All right. So with that said, this is 2. And then, considering the presence of power sources, determine the number of node voltages and independent mesh currents. So the number of independent node voltages is given by the formula n minus m minus 1. So n is the raw number of node voltages that you see. M is the number of sources. So this is sources. This is just the raw number, the one we counted earlier. Raw number. And this 1 is to actually indicate the ground. Okay, so if you're curious, what is that 1 always there? It's always there because we have 1 ground. Okay, so earlier we counted 6 nodes, right? So this is 6. And then how many voltage sources do we see? So we have 1, 2. So 2 voltage sources. So it would be 2. So 6 minus 2 minus 1. 6 minus 2 is 4. 4 minus 1 is 3. Okay. So next, the number of independent meshes. So this formula is given by n minus m. N is again the raw number. So this is the raw number. And m is the number of sources. Current sources to be exact. So we know the number of meshes is 2. And the current source is only 1. So this will be 2 minus 1, which is just 1. And that's it. So that was quite simple. Okay. Right, then minimum set of equations for the node voltage method. So remember, the node voltage method uses the KCL, okay, KCL, not KVL. It's counterintuitive. So if you're asking for no voltage, you use Kirchhoff's current law. So, first, node voltage is used to find the values of the voltage of each nodes, right? So let us see if we can immediately identify each value of the nodes first. So what do I mean by that? So let's take a look at this one, for example. Since it's connected to the ground, immediately I know it's 0 volts, right? Now, let us go over to this one. Can I tell the voltage value? Yes, I can. Because of this voltage source. Now, the voltage source creates a potential difference of 10 volts across here, right? 10 volts across here. And then remember, you must take care of the orientation of the voltage source. So it says here a positive terminal and a negative terminal. So it means it is high. The terminal here, this terminal, is higher by 10 volts than this other terminal. So that means here is higher. So that means 0 is higher, right? Higher by 10 volts compared to this node voltage. So I can reverse that and I can say that this terminal is 10 volts lower than the 0 terminal, the ground terminal, right? So if it is 10 volts lower, 0 minus 10 will give me negative 10 here, negative 10 volts. Yes, it can be negative, okay? So I'm going to recap again. This voltage source fixes a 10 voltage difference across the terminal. And because the plus terminal indicates it is higher, and the negative terminal indicates a lower voltage value, that means 0 minus 10, so this should be negative 10 over here, okay? Same over here. This voltage source shows that the terminal here is 10 volts higher because of the positive terminal. The positive means it is higher. So this end is 10 volts higher than the ground terminal over here. So 0 plus 10 is positive 10 over here. Okay, positive 10. So that's all the voltage values we can tell. We cannot tell this one because we don't know the potential difference across there. And same for here. We cannot tell the potential difference across here. So this cannot be known. Not yet, at least. Not yet. So that's it. We have 3 unknowns. So let us label these 3 unknowns. Let us call this VA. This one as V. Okay. This one is VB. And this one is VC. Okay. So we have 3 unknowns, meaning to say we need 3 equations. So what are the 3 equations? Again, remember this is node voltage method. So we have to use KCL. So let us start from this node. So when you do KCL, you're taking currents going in and equating it to currents going out, right? But we don't know what's the direction of the currents through each what do you call this? We don't know the direction of currents from each node, right? So let's say I focus on this node. We don't know the currents going in and the currents going out. So what do? We just assume that they all move out of the node. So they move out of this bubble, they move out of this bubble, they move out of this bubble, right? So let us focus on the top one here. This current is going out, this current is going out, this current going out. No current is going in. So when I write current going in, so let's say KCL of A, of node A, right? Which is the currents going in equated to the currents going out. So actually the currents going in is 0, right? There's nothing going into the bubble. So this is actually 0. And the current going out is what? So for each current going out, we had to express it with delta V over R, right? And delta V is V start minus Vn. And R is just the resistance it passes through. So when I look at this, when I look at the top current here, it starts at VA. Sorry. It starts at VA and ends at VC, right? V start minus Vn means VA minus VC and divided by R4. So let us write that down. I'm going to straight away substitute in the value. So VA minus VC divided by R4, which is 10. Then we go to the next current. So the next current is, let's focus on this one, right? So where does it start and where does it end? It starts at VA, it ends at VB. So V start minus Vn is VA minus VB. So this is VA minus VB. And the resistor that it goes to is also 10 ohms. So just divide by 10. Plus, uh, the last current is this one. So it starts at where? It starts at VA. It ends at it ends at this negative 10 volts, right? So V start minus Vn is VA minus negative 10, right? Remember, it ends at negative 10, so you have to minus 10. So that will be, let me just draw like the current. So it will be VA minus negative 10 divided by 10, right? It goes through a 10 ohm resistor, okay? So if you want to simplify this, you can multiply both sides by 10 to get rid of the denominator. You should get VA minus VC plus VA minus VB plus VA plus 10. Then you simplify this, or you get, okay. I'm gonna skip the simplification. Okay, you can just add the terms together. So add this, add this, add this, and then move everything to the correct sides. You should get negative 10 equals to 3VA minus VB minus VC. So keep in mind this is our first equation. Okay? Then what else? We need to take KCL at B. So let's focus on B, the node B. Again, okay. So for B, we know this current's direction, right? Because of the current source, it tells us that we're going into here, right? This current is going in. So we know the current going in is 2 amperes. Now, we don't know this direction of current, right? Just assume it moves out. So assume it moves out like that. Okay, so now we can take KCL at B. So KCL at B is what? So current going in is 2 amperes, right? And the current going out is what? Okay, starts at B, ends at A. So V start minus Vn is VB minus VA. So VB minus VA divided by 10 ohms because the resistor is 10 ohms. Yeah, it's 10 ohms. So you should get VB minus VA equals to 20. So this is your second equation. Now KCL at C. So let's focus on C. So just assume the direction moves out. So moves out of here and moves out of here. So this current starts from C and ends at A, right? Starts from C, ends at A. So V start minus Vn is Vc minus Va. And then what about this current? This current is Vc minus positive 10. Okay, and they both move through a 10 ohm resistor. So with that said, the KCL at C is KCL at C is Vc minus Va divided by 10 plus Vc minus the positive 10 divided by 10 equals to 0. You can simplify this, multiply both sides by 10, and then you add up the terms together. You should get minus Va plus 2Vc equals to 10. Now, for now, they didn't tell you to solve the equation, right? See, without solving. So we'll come back to this later. We'll actually need to solve it later. So question C says, use the mesh current method now and set up the equation. So mesh current should be easier because there's only 2 meshes. Now, offhand, the most immediate thing you can do is to use the mesh current. Okay, let me just clean this up. So you can immediately use this current source. So we're gonna write an equation that describes the current source, right? Now, let us assign the direction of each mesh current first. So assign it to be clockwise. Okay, we don't know if this direction is correct or not, but we just assume it to be clockwise first. So this is IA and this is IB. Now, you see what the current source tells me is that there is a net current moving up through this branch, right? There's a net current moving up through this branch. Now, look at IB. IB is the one that is going upwards through this branch, whereas IA is going down. Okay, so the net current is actually IB. See, IB is going up minus IA because IA is going down. That's why we oppose it. IA is opposing IB, so we minus IA. So IB minus IA is equal to the 2 amperes described by this current source. So that's our first equation. So from the current source, I'm just going to draw it out like this. We know that IB minus IA is equal to 2 amperes. Then what else? Okay, because this question involves a current source between the two meshes, right? It's exactly between the two meshes. This mesh here and this mesh here, which is not good, right? Because we cannot take the individual KVLs then. If you try to take a KVL, then you'll be stuck. You don't know how to describe the V of the current source. Okay, you don't know how to describe the V of the current source. That's why we must use super mesh to avoid current sources which are between the which are in the common branch of the meshes, right? So we're gonna use super mesh. Now, how to use super mesh? We're going to take the super mesh around the current source. You see, the point of the super mesh is that I skip this branch. Okay, let me just say, I skip this branch which has the current source, right? So this super mesh will help me skip the current source. So let's take a KVL around the super mesh. So let's start from here. Okay, start from here. If we go one round and come back all the way to the blue dot. Okay, so let's just do that. So KVL super mesh. So the KVL the super mesh says, okay, first I go through the voltage source, right? So see, I'm going from the positive terminal to the negative terminal of the voltage source. See, going from the positive to the negative terminal means I have a voltage drop. Okay, positive is higher, negative is lower. So a voltage drop means minus 10. And then after that, I go through this resistor. Okay, resistors always dissipate current. Sorry, dissipate energy. It's always a dissipation. So I minus it. There's a drop in potential. So again minus. And then same for this. I go through here. It's also a minus. I go through here. It's also a minus. And I go through this voltage source. It goes from minus to plus means I go from higher to lower, so it's a voltage drop. So it's always a voltage drop all around. Okay, and if you want to describe the voltage drop across resistors, remember you use the formula delta V equals to I times R. Okay, so for example, let's say for R2, what's the current going through R2? It's IA, right? It's IA multiplied by R2, which is 10 ohms. Actually, in fact, all the resistors are 10 ohms, right? Yeah, 10 ohms, 10 ohms, 10 ohms, 10 ohms. Yep. So whenever you see a resistor, it's just 10 ohms. So for R2, the voltage drop is IA times R2. Now, what about, for example, R4? So the current going through it is IB, right? This time is IB. So IB times R4 will give me the delta V of this resistor. Okay, but remember to put the negative sign because it's a voltage drop. So with that being said, let us see this. So this is minus 10 from the voltage source, I times R minus, okay, this is I times R minus I times R minus, again, the last voltage source equals to 0. So don't forget this negative sign, this negative sign, this negative sign, this negative sign. They all indicate a potential drop due to going through a resistor. Okay, so when you simplify this, you should get minus 10 IA minus 20 IB equals to 20. Okay, so let's call this equation 4 and let's call this equation 5. Okay, we don't need to solve it for now. So Based on the numerical values given in figure 1, determine the voltage source at each node and the current in each resistor. You hint is that you might want to make good use of the equation derived in B and C. So what does that mean? Essentially to get the voltage at each node, right? Just solve 1, 2, and 3, right? Just solve the equation that we got earlier. So this is what I'm talking about. 1, this one, 2, and 3. You solve this, you should get the voltage at each node, which happens to be, let me see my solutions. So I got 10, 30, and 10. Next, we want the current through each resistor, so just solve the current, what do you call this? The mesh current method question. So solve 4 and 5. You should get IA equals to -2, IB is equal to 0. Now they look like funny answers, right? What the heck? Mesh current with 0, mesh current of -2, but no, they're real, okay? This is the correct answer. Okay, so just to recap, this is the equation 4 and this is equation 5. So you just solve that, use your calculator, okay? You can make use of the calculator here to solve these simultaneous equations. Okay, so what does the negative mean? The negative means that I just assumed the wrong direction. Yeah, the magnitude is correct, it's 2, but the thing is, it's in the opposite direction of what I assumed. So, earlier I assumed it to be in the, see, I assumed it to be clockwise direction, right? So what the negative is telling me is that it's wrong. In reality, so let me just clean this up. It is moving this way. I'm just gonna clean up this also. So it is moving actually in this direction, anti-clockwise, with a magnitude of 2 amperes. Okay, and then apparently what the results tell us is that IB is equal to 0. So there's no mesh current, there's no current flowing through this mesh at all. So it's a funny phenomenon, but it really is, the math works out. Okay, so let us go back down. Okay, so these are the answers for D. And based on the numerical values, find the power generated, dissipated, and prove that power conservation is satisfied. So, what I suggest to do here is that you stick to the convention that I've talked about since the start of the semester. Okay, so those videos with the blue thumbnails, I did cover this actually about power generated and dissipated. So we use the formula P equals to I delta V. We will use this strictly. Okay, strictly. I know there are alternatives which is like P equals to I squared R or P equals to V squared R. But the problem with this is they don't tell you whether it's power generated or dissipated. They don't tell you. Okay? So I suggest strictly to follow this I delta V. This will help you, but these two will not help you in telling whether it's power generated and dissipated. Now, when you use this formula, right, you must use this delta V as V star minus Vn. Strictly again. Okay? When you put it as V star minus Vn, regardless if it's positive or negative, okay, the positive and negative will tell you whether it's dissipated or generated. So you must strictly follow this, use this formula for power. So P equals to I delta V, and delta V you must use V star minus Vn. Whether it's positive or negative, you leave it be. The sign, the polarity, whether it's positive or negative, will tell you whether it's power generated or dissipated. Okay, so let's just show what I mean. So for example, we have to look at each device of this diagram. So what did I start with? I started with the voltage source here. So we look at each of the circuit elements that we see here. So that means this one, this one, this one, this one, this one, each and all of every one of them. And then we find their P equals to I delta V for all of them. So P equals to I delta V for each of them. So let us start with the voltage source here. So the voltage source PV1 is equal to what's the current going through this? The current going through this is the 2 amperes that we know. Now, delta V is, remember, V start minus Vn. So in this mesh current, right? See, this mesh current, it goes through like this, starting from here and going through like that, right? It's going in the anti-clockwise direction, So as it goes through the anti-clockwise direction, it starts from here and ends at here when it passes through the voltage source, right? Starts at here, ends at here, means V start minus Vn is minus 10 minus 0. So this is minus 20. Okay, now let us do for PV2. PV2 is what? So PV2 is actually 0 because remember, there's no mesh current here. So what is the I delta V? Remember, it's I delta V. This is just 0. Okay, so that means PV2 is actually just 0. Now let us look at the current source. So the current source is, okay, we actually found VB. Remember this VB? We found it earlier to be 30. Okay, so keep that in mind. This is positive 30. So the current through the current source is just 2 amperes, right? Because it says 2 amperes, so it is 2 amperes. So 2 times. Now, what is the potential difference? The delta V. Delta V is V start minus Vn, right? So it starts from ground. Starts from ground means 0 minus, it ends at 30. So minus 30. So this is minus 60. Okay? So that's the power due to the current source. Okay? Next, who are we looking for? So let's look at the resistors. So the resistor, this one, I delta V, right? So the current going through here is 2 amperes, right, from the current source. So the current is 2 amperes, and the delta V is what? So remember, see VA, right? This is the node at which it ends. It starts at here and it ends at here. This is actually VA, and earlier we found that VA is what? VA is 10, right? So it's 10. Let me just check. VA is 10, yeah. It starts at 30, it ends at 10. So that means P of R1 is actually, so the current is 2, and delta V is V start minus Vn. So 2 times 20 is 40. So this is positive 40. Now, let's look at PR2. So where is R2? R2 is here, right? So the current going through here is this 2 ampere, it's still this 2 ampere, right? This 2 ampere. So it goes through like this, starts from here, it ends at here. So this is 2 amperes times the delta V is V start minus Vn. It starts at here, which is VA, right? VA is 10 ohms, and it ends at here, minus 10. Yeah. So I delta V is I times delta V is V start. It starts at 10. It ends at negative 10. So minus 10. Yes, please keep this in mind. So this is 10 plus 10, which is 20. 20 times 2 is 40. Okay? Now let's look at PR3 and PR4. So remember, this mesh has no current, right? And remember, to find power is I delta V. If there's no current, meaning that I is 0. If this is 0, then that means P is equal to 0. So for both R3 and R4, since there's no current here, there's no current passing through them, means both their powers are 0. So we know that P R3 is 0, P R4 is 0, because there's no mesh current flowing through them. Okay, and that's all. That's all the devices that we see here. Now that we get all these values, right? So what should we do to prove power conservation? To prove power conservation, we need to show that all the elements, right? When you add up the power, it should be 0, because there's no creation or destruction of energy from the whole source, from the whole circuit altogether. So what do I mean? You just take all the values that we got, so this plus this plus this plus this plus this plus this plus this. If you add it up together, it should give you 0. Now let us check. Okay, so if I add it up, I will not write down the zeros, right? Because the zeros do nothing. So total power. So we got minus 20, minus 60, plus 40, plus 40 equals to, you see, this is negative 80, this is positive 80. So altogether, they will give me 0. So power is conserved. Now let us make more meaning of the power that we calculated. See these negative signs, right? This is actually power generated. So this is due to the sources. Whereas these are power dissipated. So we have 80 watts being generated and 80 watts being dissipated. Altogether, there's no creation or destruction of energy. So that means power is conserved. And that's why you find out all the powers due to the elements, including their signs. So that's why you must use the P equals to I delta V. And remember, delta V is V start, V start minus Vn. So V start minus Vn. Keep the signs, whether it's positive or negative, do not freak out, just keep the signs. And then when you add it all up, it should give you 0. That's the beauty of using this technique. Okay, so you can show that power is conserved. If your power is not conserved, that means something is wrong. Okay, it's always conserved, always. Okay, so let's move on.